Working within this emerging field of soundscape ecology or ecoacoustics. Within ecoacoustics, which is a very recently framed term and emerging field, the sound is seen as both a resource and a source of information. So whilst bioacoustics has been studying sound as signal and meaning between creatures for a long time, these fields of soundscape ecology, which is the sonic version of a landscape ecology, which is looking at this very high, wide level, and trying to understand, in evolutionary terms, sound is a resource. So creatures need to hear each other in order to mate. Is the bottom line. Because it's a resource, they compete for it, and they therefore structure their environment. Yeah. So through competition, we structure our environment, which means that if we can learn to read back the environment, we can learn something from it, right? So the world affects me and I affect the world. And therefore the world is a kind of a history, a record of my interactions with it and my interactions with other things in it. So the logic of ecoacoustics within soundscape ecology is that actually this, similar to what Dan just mentioned, where a musical track is structured consciously in time in terms of beats and notes, etc., or maybe not, maybe in free improvisation, it's a little bit more around the hypothesis here, the acoustic niche hypothesis, which has been put forward by an ex-musician, in fact. The idea is that in a stable, healthy habitat, these creatures have been sharing this space and have learnt to play nicely, if you like, that there's an acoustic niche. So just in that they have a behavioural niche and a physical and biochemical niche, they have a sonic niche. So that this is a spectrogram. Hands up if you've never seen a spectrogram before. Okay, so this is time. It's like, you think of it like a heat map, like a topographic map. Time along here, frequency up here, and the brighter it is, there is more energy in that frequency band, right? So we could probably go around the room and try and recreate the sounds of this from a spectrogram. So the gibbons are going, there's some birds going, and there's some insects going up here, right? So that's and then we've got maybe a bat. I'm not quite sure why there's up there. There's up here, you can't even see, it's too low range, but this is probably like 0 to 20 kilohertz, something like that. Okay, so this kind of hypothesis, which isn't quite a scientific hypothesis, it needs a bit more work to make it kind of verifiable and testable, is that by listening to the overall structure, like a composition, like a whole orchestral arrangement, we can understand something about the ecological health of the habitat. Lovely. Okay, so if we could make some devices, some little microcomputers that we could drop in, maybe with drones over the whole Amazon, and they could sit and listen in the trees and monitor, and then they could just text us every day or every week or every month the health of the habitat. And this would totally revolutionise biodiversity monitoring. We could look at the impact of oil drilling in the Amazon. We could look at the impact of our lovely new reserves we've made. We can have readily evidence-based land use policy, etc., etc. But the trick, of course, is that how on earth do we formalise that? So we might be able to look at this and say, and we might be able to listen to it. So Bernie Krause, this guy who came up with it, said, yeah, I can listen to an environment. I can tell by listening to it, how it is. Well, how on earth do we formalise that? That's a whole other line of research. So in order to, like we developing any new tool, we compare it to an existing tool. Okay, so we have a ground truth, and we have a putative new measure that we want to validate. And we validate that by collecting a bunch of data, comparing the two, and getting a result. And this is what we've been working on. So we went out, we've got some sound recorders, we programmed them, you strap them to a tree, you program them to record 1 minute every 15. I also recorded the dawn and dusk and midday choruses, just for kicks. And then you put a bunch of them out over 1 kilometre, in woodland, in different habitats. And you do this in different situations. So we did it in ancient woodland in the UK, and a regenerating, rewilded farm, and a current farm, which is a monoculture crop. So we did that in the UK, and we also did it in Ecuador. There's not loads of these guys, but there are some. So we did it in primary Chacon forest. We did it in secondary forest. These are some of our, he was the chief in the Amazon who helped us. And again, in a palm oil plantation, a kind of monoculture. So we've got a strong environment a gradient across environment, we've got a gradient across time, we've got 2 ecotypes. So basically we should have some shape in our data. And we've got loads of data. So we collected each of these sites, we collected 16 recorders for 10 days, recording 24/7. So we've got about, once we've cleaned it all up and just kept the mono versions, we've got 175,000 1-minute files. Okay, and then we want to look at some possible ways of measuring biodiversity through sound. Okay, that's our first question. Can we use sound as a proxy for biodiversity? And we developed some new audio features. So we've been talking a little bit about this already. And rather than doing anything nearly as complex as what Dan's doing, we're looking at really, really simple ones to begin with. So we might be, this is a time domain representation of sound, but it's a kind of an envelope of that. So we can describe this, we can create some statistical summaries of the time domain, and then if we also look in the frequency domain, we can kind of simplify it a little bit and think about the energy distribution. So here, this is just the same as, instead of being brightness on the y-axis, I've now got a bar chart. So this is again a sound which has got a lot of mid-range frequencies higher in it, and we compute a bunch of indices which describe. So indice here is the same as audio feature. Describe the frequency domain. And then we've got a whole bunch of numbers that we need to work out if they're real or not. And then we need something to compare it to, right? So we get some very dedicated and keen ornithologists, specialists, especially in Ecuador. There's only like one person who knows all the birds in that area. And they sit and they listen to about 2,500 samples of 1-minute audio files, and they give us essentially this for up to about 60 species. So in that 1 minute of recording, how many rufous motmots did they hear, and how many slate-throated whitestarts did they hear? And then we compare the two, right? So it's simple. You have an old way of measuring things, and you have a new way of measuring things, and you compare the two, and there you are. So you can do that. So you can look at a correlation, is the obvious thing. You say, what was the abundance? How many species were there in sample A, according to the person who sat and listened to it? And and if I look at that over my, how many, 2,500 is the subset of labeled data, do all the acoustic indices which were low valued, are they the same ones as the species distribution which is low valued? And yeah, for ecological data, it's pretty good. We're up in, this is 40, 80%, so this is like 60% correlations, and I haven't put stars on, but almost all of these which are high are significant correlations. So that's sort of good, but these are just summaries, so we can't really tell whether that is definitely telling us anything about the birds, or is there a correlation just because, I don't know, it was windy that day and the birds were quiet, or the human couldn't hear the recording because there was a plane going overhead, and so nor could the recorder. So there's a whole bunch of other stuff. We need to unpick it a little bit more. So then we might want to look at, instead of doing averages of it, we might want to look at all of the acoustic indices and all of the bird species. But we've got 26 indices and we've got 60-odd species. So like Dan was talking about, trying to visualize high-dimensional data sets is notoriously tricky, but there's some bit of maths we can do, and we can kind of reproject high-dimensional data sets. It's just a bit like having a shadow of your hand on the wall. I can turn my hand around until I can sort of see a sensible representation in 2D. So we can see there's structure in the bird species. So this was the primary, the secondary, and the palm oil plantation. So there's some structure there, so that's good. And we can also see some structure in the acoustic indices. So it's pretty messy, but for an initial look-see, there looks like there's some differences. So then what we can also do is build a model, and now we're starting to get on to really the similar sorts of tools that we use in machine learning. So this is a part of a random forest type approach, and in ecology this is really nice because it can tell us not only was there structure in the species data set, was there structure in the acoustic data set, but of that variation, of the differences in the observed species across habitats, how much of that can be explained by the acoustic indices. So we can start to say, can the acoustic indices predict biodiversity, which is what we want in a tool, right? That's what we want from our new tool. So that all seems pretty cool. And then and what this also gives you, the random forest algorithm also tells you, it can kind of quantify the contribution of each of these indices to describing that. So that's great. And then what you do is you get a list out of it saying the variance of the RMS explained this much of the variance observed in the species, and this did this, and this did this, and this did this, and this did this, and like, that's great. And that's sort of what's generally reported, full stop, the end, thanks very much. But if we want to come back and say, well, but actually, what does the variance of the RMS, what does that really tell us in ecological terms? What does that really mean in terms of the changes in the composition of that bird community over time? Again, is it because of the bird species, the community composition? Is it something to do with the way the trees reflected sound? Is it something to do, again, with the other anthrophony, the noises that were made by nearby? We really need to be able to interpret these results. So it's not just enough, I would say, to make these statistical comparisons. We really need to understand what they mean. And then this is a bit problematic because necessarily to build a good model, we need enough data. We need so much data that it's beyond listenable compass. I can't go back and listen to 175,000 1-minute audio files. I've been trying. I put it on in the office and I put it on at home, and I'm trying to get a feel of, like, was there more tractors in the farmland, or, you know. And this is the problem, right? This is always how we've done science. So, and it's the same with machine learning now. It's like these methods have been around for a really, really long time. But maybe, I'm not sure, but maybe what's happening is actually we're becoming further and further. We've got more and more and more and more levels of abstraction. Certainly that's true, say, of deep learning. So what we're studying, what we're interpreting, and what we're publishing is this kind of plot, slightly abstract plot of a statistical test or kind of mean squared error or something, which summarises a sort of multivariate statistic, which is calculated on an audio feature, which in turn is derived from digital recording, which was made of the acoustic environment. Yeah, so we've got a visual representation or a single number that's representing a statistical summary of computational derivation of a digital representation of the acoustic environment, which in itself is only part of the actual rest of the community, right? Because they weren't all making a noise. There was loads of other birds that weren't doing anything, or worms, or caterpillars, all sorts of things. So it's not exactly a black box, but it's not terribly transparent, right? So we've got the world, and we're trying to learn something about it and understand it, and ideally predict it by making this model of it. But sometimes this gets a bit convoluted, and we can't necessarily get back and understand it and verify it. So one thing to say is that humanizing algorithmic listening might mean, and I'm warming this is a prompt because you're going to be playing this later on, it might mean taking full responsibility for properly understanding the models that we're making and unpacking them and being able to interpret them. So what I'm planning to do next is to go from, and it strikes me, it is a bit ironic, and I think, Sharon, you brought this up in one of our workshops, we were saying, we want to treat audio as audio with oral history. But we're not. We're treating audio as a bunch of numbers and a scatter plot. So sometimes in this situation, in ecoacoustics and possibly in oral history as well, we actually want to listen. You know, all these ideas have come from listening. And as musicians or field recordists, it's really engaging. Like being situated in listening that's where you've learnt something from, by listening, right? And we need these kind of powerful statistical toys to play, or tools and toys to understand these big data sets. But if we're going to then apply those results for kind of impactful decision making, then I do think we need to take responsibility to understand them. And one way I'm thinking about doing that, it's a bit naff, but I'm calling it ecospectralism, is to think, well, can we then use methods from spectralist composition or experimental computer music, as well as possibly interactive arts and gaming, to create listening experiences that preserve the kind of rich, situated experience that we have when we're sitting in the field or we're playing music, but achieving the kind of oversight and perspective and the power machine listening. So can we, instead of making statistical summaries of tests, can we make audio summaries? So very simple things of doing mean spectrum analyses and sonifying them. Or are there more kind of sound-based statistical summaries that we can use that can give us this kind of overarching, rapid exploration, but still kind of be engaged with it? So that's sort of something I'm thinking about next. And when Fiona mentioned, even the question of is half a tape silent? I mean, I guess visualizing that you could rapidly see, but there might also be all sorts of other tools, and maybe this is an errant machine listening algorithm, I'm not sure, other than just playing everything at high speed. Maybe there's some slightly more sophisticated ways of summarizing audio in the audio domain so we can kind of rapidly hear things. Yeah. Thank you.